All right. Then up here, from 4 to 7, my position doesn't change. And so my velocity is going to go back to 0. All right. Then over here, I've got, this is much slower. So it looks like between 7 and 9, the position changes by 1 meter. So over 2 seconds, it changes by 1 meter. So I'm going to calculate my slope there. I'm going to say, what's my displacement? I'll say V is V of T here, okay? So my initial position, that's going to be XI minus XF divided by delta T, and that's 2 seconds. So delta T, that's 2 seconds. So down here, I'm going to put in my numbers for there. All right, so my initial position. My initial position is 3, and it goes to 2. So I'll have, it'll be 3 minus 2. So 2 minus 3 right there over my time. So that's 2. So my velocity then is going to be 0.5 meters per second, and it's negative. Okay, so that's going to be right here. So from 7 to 9, it's going to be minus 0.5. Okay, so that is how I go from. Someone's calling me. All right. There we go. Do not disturb. All right. So then if I look at my my graph over here, now I can say, all right. So for this period, I see that my position is changing, and yeah. So I created my velocity versus time graph from my position versus time graph. Okay. So let me get up another example. All right, let's draw another picture. All right, so what if I have a velocity that looks like this? So this is going to be velocity versus meter versus time. All right, so what if my velocity looks like this? So this is velocity versus time. Okay, so where is my, let's see, let me ask you guys some questions about this. All right, during what segment is my velocity not constant in this graph? Somebody tell me.
From like 2 to 3 seconds?
Yes, from 2 to 3, it is not constant. From 3 to 4, it is constant. And over here from, let's see, that's 1, 2, 3, 4, 5. From 5 seconds to 7 seconds, it is not constant. All right. And where is my object slowing down? Where is the speed decreasing on this?
From 6 to 7, or 6 to the end.
Yeah, so from 6 over to here, well, from 6, so it's getting slower. Yeah, so from 6 over to right here, the velocity is decreasing, and so it's getting smaller. When I go from, let's see, from this is 2, 3, 4, 5, 6, 7, 8, 9. So from 6 to 7, the velocity is increasing negatively. It's becoming more negative. So right here, this is the segment where the velocity is decreasing. Okay. So you should understand how to do these graphs with velocity versus time, acceleration versus time, and displacement versus time. Okay, so let's say here I have a
Dr. Wispy.
yes.
So would you say it's decreasing from 6 to 7 or it's increasing for velocity?
So on this graph here, it is from 6 to 7. The velocity is getting more negative. So it's like it's you could say it's increasing in the negative direction. Okay.
Okay.
So from over here, this would say, all right, right here, your car has a constant positive velocity. So it's traveling in the positive direction. Then it's from 5 over to 6, its velocity is decreasing because it's moving more towards 0. This is 0 here. 2 minus 1 minus 2. And then from over here, from 6 to 7, it's like your car turns around and goes the other direction, and its velocity, the magnitude of the velocity is increasing in the negative direction. Okay. Does that make sense?
Yes. Thank you.
All right. So let's see what else I got on my list here. All right. So what if, I think you had a homework problem about this, and that was, what if you have a plant growing? All right, so a plant growing. How can we calculate the velocity of a plant growing? Somebody tell me. Well, let's use the example of maybe I plant these little baby trees in my yard. They're American sweet gum trees, and I have a big sweet gum tree in my backyard. And last year, my sweet gum tree was 3 inches tall. Okay. This year, right about the same time, my sweet gum tree is my baby tree that I planted. It has more leaves now, and it is 5 inches tall. How do I calculate this? It's growing, the velocity that it grows in meters per second.
You can calculate the displacement, so like 5 minus 3 over the amount of time, and then convert it to meters per second.
Yes, that's exactly right. So if I give you, if there's some plant growing and it's in standard, you need to convert it into meters per second and then get a time. So let's do this, because my son was actually asking me if I've been alive for 1 billion seconds. And so I had to calculate that today. I have been alive for over 1 billion seconds, but let's do this example real quick. All right. So that would be, its final is 5 inches minus 3 inches. And that's going to be its velocity for 1 year. And so in 1 year, there are 365 days. There are 24 hours in a day. There are 24 hours. There's 60 minutes in a day times 60 seconds in a minute. And how many inches are in a meter? Because we want meters per second. Does anybody remember? Remember the clock tower. How do we quickly convert meters to inches? Well, I remember 1 yard is roughly equal to 1 meter, right? But I know in 1 yard, there are, and this is just approximate, but we're gonna do it for real. All right. So in 1 yard, there are 36 inches. There's 36 inches, but I remember in 1 meter, there are 39 inches or thereabouts. Pretty close. I think it's real close. Okay. So make sure you write down these conversions on your card. So let's just assume that I'm right. There are, actually, let's look it up because I don't want to tell you the wrong thing. All right. What's the actual conversion? Does anybody? 1 inch. All right. I do remember. So 1 inch is 0.0254 meters, but let's just calculate am I right? Let's see, 39 inches in 1 meter. Oh, that's actually about right. Yeah, that's really close. All right, so just remember 1 inch and 30. If you say, all right, a meter is 39 inches, then I got 1 over 39. That equals 0.0256. So I was really close, but this is actually better. So then you'll need to convert that into meters, and you'll say, all right, 1 inch. So 1 inch is 0.0254 meters. All right, so you got to do the correct conversions. Oh, I didn't do that right. This should be to power of -1. All right, so there we go. Hopefully you can. So you need to be able to convert, right? All those conversions, convert from inches to meters. Make sure you know how to do that. Let's see what else is on the list. Yeah, so convert distance into and out of meters. Calculate the speed a plant is growing. Then also you need to be able to find a displacement vector. We did a lot of those. There was a problem with the girl on a bicycle, and she went on those crooked streets. So you need to be able to find a displacement vector and then calculate a displacement vector of velocity or acceleration. What's the formula for how do you find delta x? What's delta x? It is x final minus x initial. Then my velocity, delta v, is xf, or it's delta x over delta t. And actually, this is my average velocity. So it's delta x over delta t. So this would be my my final time minus my initial, and then my final position minus my initial position. If I want to find my average acceleration, then I'm going to say, all right, I'm going to do the same thing, but with velocity. So it'll be my final velocity minus my initial velocity divided by my final time minus my initial time. Okay, so hopefully you should be able to calculate velocity, displacement, and acceleration. Let's see. Yeah, so those, I think those are going to be the main topics that are going to be on the exam. So it's finding displacement, velocity, acceleration, and I think that's pretty much all that we've covered. And then, of course, you need to remember your trig identities. So if you have something where you need to find the different components or the angles, all right, so let's go back and review. Let's say someone is flying a drone, and so here's my drone. All right, there's my drone. And let's say the drone starts up at 36 meters and it flies downwards. And it moves down to a new height of, let's say, 10 meters. And it travels this way. So here's my starting position. And it goes from 1 meter over here to 15 meters. All right. So I'm going to test you guys. Okay. So here's this is my drone. It's a quadricopter or something. I don't know. There it is. All right. So if my drone is flying like this, then I might ask you, what is the displacement that my drone travels? So what's the displacement? And what angle? What angle is it? Is the direction of that displacement? So what's the angle of my displacement? And I want you to, and I'm going to say measured from horizontal. All right, so why doesn't everybody try and calculate that real quick? Let's calculate it right now. Oh, we got some questions in the chat. Let's see what people said in the chat. Oh, why is 5 to 6 a decreasing velocity? Oh, this was, I should have answered this before. Isn't it still positive and just acceleration decreasing? Oh, let's go back and look at that. I'm sorry I didn't get that. All right, so let's go back to our plot here. I think it was about this one. Someone asked, from 5 to 6, why is the velocity decreasing? That's a great question, because from 5 to 6, the magnitude of my velocity is +2 and the velocity goes to 0. So that means over this time period, it's decreasing. It is positive. Yeah, we have a positive velocity here, but it's decreasing. So it's getting smaller, but it's a positive velocity. Once the velocity gets over to here, then it's becoming more negative. Okay, so the magnitude is getting larger, but it's in the negative direction. So we have a negative velocity over there. All right, so here's what I want you to do, guys and gals and everybody. Okay, I want you to calculate this real quick. So let's take 5 minutes and calculate it, and then I will go through it. Okay. Well, I'll start going through it right now. But this is the kind of problem you should be able to solve, because if you understand this, you should be good, because this is displacement vector. So take 2 minutes and try and calculate it. Now remember, I want you to calculate it from the horizontal. And I want you to go counterclockwise. So from the horizontal, go counterclockwise. Tell me what the angle is. Sorry, I didn't specify that, but that's what I meant. Okay, let's go through this one, and then I think that should be good for the review. Okay, so let's take a look here. Oh, we can do it down here. Okay, so we definitely have a triangle here. I think we go from, let's calculate our displacement. We go from in our Y position. This side is we're gonna go 26 meters downward, and then we're gonna move 14 meters across. So we'll say that that's our hypotenuse. So we'll say that C equals 26 meters squared plus, and it moves 14 meters this way. So 14 meters squared. Okay, so that is the magnitude. And then let's look at how we would calculate that. All right, so I can get this angle right here, and I can do that using tangent. So I'll say, all right, tangent of theta is going to equal that's going to be my Y is 26 divided by 10. That's X. Okay, so my meters are going to cancel. Okay, and I'm just using this as a triangle. So first what I'm going to do is I'm going to get this angle here, but then I'm going to subtract it from the angle going that way. Okay, so I'm going to take the arctangent of this. I'll say theta is equal to, I'm going to take the arctangent of this side. So it'll be tangent, the arctangent of 26 over 10. Okay, and you probably have to use your calculator to do that. Maybe if you're really good at trig, you can just remember that. But if you're like me, you got to use a calculator. Okay, so hopefully you have your calculators ready. Remember, you need to bring your own calculator tomorrow. So bring one that works. Make sure the batteries are fresh. And let's calculate this real quick, and then I'll let you go. All right, so increases. All right, first I'm gonna do so the hypotenuse of my triangle is going to equal, I need to get my math palette, basic math. All right, where did my palette go? All right, I need the square root symbol. There's a square root symbol. All right, 26 meters squared plus 14 meters squared. Right, so that's going to be, oh, and I forgot to put in a decimal. So it gives me there we go. That's going to be, I calculate, it looks like 30 meters about. Yeah. So I'm going to keep that in there. So that'll be, yeah. So H, my hypotenuse is going to be 29.5296, but I need to round that off. And so I'm going to round that off to 30 because this will just round up. So this will be 30 meters there. All right. That's going to be a 30. Then I need to get my angle, and I need to do a arctan. There it is. Arctangent of 26 divided by 10. And then I need to put this, for me, I need to put this in radians. So I'm going to say times pi divided by 180. This is how I have to convert it in Mathematica, because I can't do degrees, which is fine. I just have to remember to type that in. And I'm pretty sure I messed that up because it was in degrees. I need to convert it into radians. That doesn't seem right. Okay, let's do it a different way. So 26 divided by 10. Okay, that's just gonna give me an angle. So I need to say, oh, I know what it is. I'm gonna say pop. Yes.
Why are we using 10?
Because I typed it in wrong. Sports. Sorry about that. Sorry, because I'm confused. Okay. I can't remember how to convert from. There we go. Now I got 61 degrees. Is that what you guys got?
Yeah, I got 61.
61. Okay. But so we'll say 61 degrees, but that's the angle right here. So that's 61 points. I said 61.6992. That's the angle right there. But I said measured from the horizontal counterclockwise. Maybe I said it. I should have written that. Okay. So that means starting from here, from this side, then I'm going to go all the way around there. So I need to subtract that from 360. All right. So let's go back here to Mathematica, and I'm going to say 360 degrees minus. Keep all those digits in there. So that'll be 298 degrees. I'm going to round that off. There's a 0.3 there, so it's going to be 298 degrees. All right. So I'm going to say 200. My angle will be 298 degrees. All right. So this is the magnitude of my displacement, and this is that's my angle. All right. So
why do we have to measure it counterclockwise?
Just because I said that to be arbitrary, because in the homework there was one problem where it asked you to calculate the angle that way. So you just need to be aware of which way you're supposed to calculate it. That's all. I mean, if in real life you could specify, which way you're going to say the angle, but you really need to, in real life, you'd have to say, all right, I'm going to calculate this going, clockwise from the horizontal. You just have to specify, because if you just said, like, the displacement is 30 meters at 61 degrees, that could be either above or below the horizontal, right? You need to, or it could be 61 degrees from the y-axis. I have no idea. So you just have to specify it. That's all. And say, which way are you measuring your angle?
So the 61 degrees is technically clockwise from the horizontal.
Yes, that's okay. 61 degrees is right. Yeah.
Or you're making us calculate the counterclockwise just because?
Yeah, because in the problem in the homework, it asks you to do that, right? So it said going from the east direction counterclockwise. So I just wanted you to, when you're reading the problem, you just need to be aware of which way it's asking you to find that angle from. Because if you have a vector, I mean, you can specify the angle, but you just need to say where you're measuring it from. Either one is probably fine. Although, yeah, I don't know if there's one convention that you would use to do that.
Okay. I have one more question.
Yes.
It was about some of the homework problems because I was wondering if they were going to be like to that length on the test. Like there are a lot of kinematic equations.
So I'm going for you to be able to be done with this in hopefully half an hour. I mean, and when I say that, that's like on average. So some people it will take 50 minutes. Some people might be done in 15. It's, there could be a very big variation. If it was me, I would probably be done in more double time because I was always super, super slow and I needed, and I just needed a lot of time. So whatever that I'm, as the professor, I'm saying I hopefully on average people will be done in this amount of time. But hopefully it'll be sooner. So the problems each one problem won't take you more than 4 or 5 minutes at the very most. And there's going to be about 10 problems, and hopefully you can finish a problem on average in 2 or 3 minutes.
Okay. My question was more like what kinematic equations are we going to need to know? Like, are we going to need to know every single one from the chapter? Because there were some complicated ones. Like for the one, I remember the one for like calculating the gnat's ability to jump off the surface of the whatever, like his instant acceleration, and then like how long it took for him to get back to the ground. Like there were some more complicated equations in there. I was wondering if we needed to know those.
Ooh, which problem was that one? Let's take a look at that one.
Yeah. I believe it was problem like 22 or 23.
All right. Give me 2 minutes. Hopefully one. Let me log into the homework and let's take a look at that problem. So that was chapter 2. Which problem?
The one I'm sorry, I don't remember the number. It was the one talking about like the gnat's ability to jump off the ground and calculating that acceleration and then like how long it took for him to get back to the ground.
Okay, let me look at that problem.
I'm trying to find it too.
Sorry, I don't know. Oh, wait. When jumping, a flea rapidly extends its legs. Okay. Reaching a takeoff speed of 1 meter per second. Okay. So what is the flea's acceleration as it extends its legs, right?
Yeah, that was the one I was talking about.
Give me just 1 second. So what equation did you use for that one?
Sorry, I'm looking for it right now in my notebook. Yeah, this is why I was asking because I wasn't sure if we needed to know this or not for the test.
Oh, okay. All right. Let me look this up real quick. In general, yes, I think you need to know there are basically 4 equations of motion. And so I would let me write down the equations. And we can look at this problem real quick, okay?
Sounds good.
All right. So when you read this problem, whenever I read a equation of motion problem, I think about when I'm picking which equation to use to solve this, I think about which variables do I know. And so this one says, when a jumping flea rapidly extends its leg, reaching a takeoff speed of 1 meter per second over a distance of 0.5 millimeters. Okay, so the thing that jumps out at me in this right away is there's a couple of things we know. We know the distance that it was accelerating over, and we know its final velocity. Okay, but we don't know the time. So since we don't know the time for this one, we have to look at our equations of motions and we have to say, all right, what things do we know about this problem? And so, my go-to equation of motion was always, or is always, I always think, all right, can I use xf minus xi equals vi times delta t plus 1/2 a times delta t squared, right? So would that be is this a good equation for this problem? Somebody said, would you accept a range of answers on the test? Well, they're going to need to be within a certain percentage of the right answer. But if you show your work, then you can get some points, even if you maybe get the wrong number. All right, so when I look at this equation, I don't have a time in my problem. So this equation is not going to help me as much. Okay, there is another equation, and that one is, it would be Vx, this would be squared, final, equals Vx squared initial plus 2ax times delta x. Now, of course, the flea, we're saying that he's jumping up and down, so you can change the x to y, and that's fine. So this is a good equation because it doesn't have time in it, right? And I do know the distance over that the flea was accelerating, and I'm solving for the a here. That's the thing that I want, okay? I know what delta x is. I was given that in the problem. It tells me, yeah, the flea delta x here is going to be 0.5 millimeters. Okay, so I know that. The initial velocity, well, since the flea is stationary, and I can change this to y because I'm going to draw a flea here. Here's my flea. That's a beautiful flea. All right, so this thing is, oh, I guess they have hinged back legs. All right, I don't know. They have big legs. There's my flea. That's a cool flea. All right, so he's accelerating upwards over 0.5 millimeters. Okay, I don't have a time here, but I have this. Initially, he's just standing still. So I'm going to say Vy initial, this is going to equal 0. Okay, and it says, what's our final flea velocity? Reaching a takeoff speed of 1 meter per second. So it gives us his final y velocity is 1 meter per second. Okay, so yes, you need to know how to use these equations of motion. Another one, a good one is, of course, x equals delta v times t, or sorry, it should be v times delta t. So x equals v times delta t. Not so much for this problem, but if there was no acceleration, then you could use this one. But for this problem, we're just going to use this one right here. All right. So I know so I'll write what my new equation is. It'll be vy final squared. My initial velocity is 0, so it's just going to be 2 times a of x times delta x, or sorry, this is y, delta y, okay? I know what my delta y is. I can put that in, but I need to convert it into meters. All right. So I'm going to say, and I know what my initial velocity is, or my takeoff velocity. That's my final velocity. That'll be 1 meter per second squared. Okay, so that's just going to be 1 times 2, then AY, that's what I'm solving for. And my distance here, I'm going to convert that into meters. So it'll be 0.5, so 0.5, yeah, 0.50, and there's a 0 there, so I have 2 significant digits, millimeters. All right, now I want to convert millimeters into meters. So this will be 1 meter equals 1,000 millimeters. Okay, so then I've got 3 zeros here. I'm going to move my decimal place 3 zeros. So I'll have 2 times AY times, then I'll have 0.0050. Let's see, 1, 2, oh, no, I should have one more 0. Oh, I messed that up. All right, so it should be 2AY times 0.0050. Is that right? I think it's right. Meters times 1 meter squared per second squared. And I've got my A there. All right, so when I do this, now I'm going to say AY, I'm going to leave that over here. AY is equal to, I'm going to divide by all this. So this will be 1 meter squared per second squared divided by a 2 times 0.00050 meters. Well, that kind of all got bunched up. All right. So now I'm going to go over here and I'm going to calculate this. Go back to Mathematica. Put this in here. So I'm going to end up with 1 divided by 2 times 0.0005. And that's going to give me 1,000. Okay, it looks like I get 1,000. So I'm going to see my units here. This meter is going to cancel with that one. And so this will give me AY is 1,000 meters per second squared. And I have got a second squared up there. Is that the right answer?
Yes.
Wow. Man, fleas are amazing. Oh, man. I think if a human accelerated, that is 100 Gs. Wow. So just think about that. If you accelerated like a flea, you would be dead. Wow, fleas are amazing. So it's 1,000 meters per second squared. Holy cow. If that happened to a human, like I said, at 6 Gs, so at 60 meters per second squared, a human blacks out. At 100 meters per second squared, you would definitely die. It would liquefy your internal organs. Wow. I learned something new. Okay. I think you guys are ready. Any other questions?
I have a quick question.
Oh.
Yes. Yes.
Sorry.
Oh no, go ahead. What is it?
So in class and in lab and stuff, we've said that gravity is 9.81 meters per second squared.
Mm-hmm.
But the textbook kept saying it was 9.80. Do you care which one we use?
No, if you use 9.8, that's fine. Technically, it's 9.81, but 9.8 is fine.
Thank you.
And, make sure you show all of your work, because even if you get a wrong number and you put that in, I'll go back and I can look and see if you did the right equation. So showing all of your work is really important. All right. There was another question, I think.
Yeah. It was on question 22 of the homework.
From chapter 2?
Yes, chapter 2.
Okay. So 22. All right. What was your question? All right, let me share the screen and we can look at this problem real quick. All right. So it says a steelhead trout migrate upriver to spawn. Occasionally, they need to leap up a small waterfall to continue their journey. Fortunately, steelhead are remarkable jumpers capable of leaving the water at a speed of 8 meters per second. Okay, so what is the maximum height the steelhead can jump? That's a good one. All right, what is the maximum height a steelhead can jump? Then in part B, it says, leaving the water vertically at 8 meters per second, a steelhead lands on the top of the waterfall 1.8 meters high. Oh, how long was it in the air? All right. So let's think about part A. What is the maximum height the steelhead can jump? All right. What equation should we use for this one?
The final velocity squared equals the initial velocity squared plus 2 times acceleration and displacement.
That sounds like a good one. Okay. Yes, because you don't know the time, right? And we know, what's the acceleration going to be?
Gravity.
Yes, that's exactly right. So we know the, hold on, I got to plug in my computer. We know what the acceleration is. We know what the final velocity is going to be. What's our final velocity going to be for that one?
0.
Yes, because at the top of the jump, the velocity is going to be 0. Okay, so let's plug in some numbers here. All right, so I'm going to draw a picture of a trout. Here's my trout. Personally, I always like to draw and make the model actually look like the trout, but that's totally up to you. There's my beautiful trout. Okay, so my trout he's going to leave the water at V equals 8.0 meters per second. Okay, so I've got one decimal of precision after the 0 meters per second. There he is. V equals 8.0 meters per second. Okay, so then I know what his acceleration is. AY equals 9.8 meters per second squared, and that's a minus because it's going downwards. So then I'll say Vy final squared equals Vy initial squared plus 2AY delta X. Okay, now delta X, I'm gonna come over here to my trout. I'm gonna say, all right, here is his final height, XF, and here's his initial height, and I'm gonna call his initial height 0. So then I just have, and my final velocity is going to be 0, because at the top of the jump, the trout is going to be frozen in the air. He's going to be up here, just hanging out in the middle of the air. Imagine this beautiful trout floating in the air. Wow. There he is. All right, he's floating in the air. And all right, so his final velocity, this is going to be 0. And so I'm going to end up with this. So this will be my initial. I'm going to bring that to the other side. His initial velocity will be, we'll say Vy. Yeah, that's, so that'll be 8.0 meters per second squared minus 2 times 9.8 meters per second squared times x final. That's the height that we're after. All right, so I'm going to subtract this from the other side, and I'll end up with 8 squared is 64. So that's going to be 64 meters squared per second squared. And now this negative sign will go away. 2 times 9.8, that'll be, well, it'll be about 20. So it'll be 19.6, I think. Oh, yeah, 19.6. So that'll be 19.6 meters per second squared times x of f. All right, so I'm going to divide 19.6 meters per squared from both sides. 19.6 meters per second squared. So this goes away. Then divide this side by 19.6 meters per second squared. Okay, well, my second squared go away. And then I've got a meter here. So that goes away. So I end up with meters. So that's good because I've got the right units. I wanted to end up with the distance. So that's good at least. I know I've got the right units, and I can see that's going to be about 3.6 about, but let me just throw that into Mathematica. All right, so I've got 64 divided by 19.6. So then its final height, just if I calculate it, I'm going to end up with a number that's 3.26531 meters, but that's too many digits. So I had one decimal place of precision. So I need to round it off right here because I had 2 significant figures. So this is going to be 3.3 meters is, oh, and I changed it to an X. It's supposed to be a Y. And that's just if you call up X, but that's fine. So my final height is 3.3 meters. Okay, so that's for the first part. As we know how long this trout is going to be going up on our trout journey. Okay, so let's now for the second part, that's the total height, but he jumps up 1.8 meters into this waterfall. Wow. And if you think about that, the fish is jumping 6 feet up in the air. Wow, that's almost 7 feet up in the air. Holy cow. So they can jump literally over your head. Wow, aren't trout amazing? Let's draw a new picture for part B here. So we've got our trout leaping up in the air. Draw another trout. Okay, we'll draw him head on this time. Here's our trout. There's our trout. His tail is sticking out here. Wow, look at that awesome trout. He's smiling because he can jump so high. All right, there he goes. And he comes back down here and lands on this waterfall. There's our trout. This beautiful, beautiful waterfall. There he is. It's a happy waterfall, like Bob Ross would say. It's a happy waterfall. All right, so now let's go back to the problem. What does the problem say? The problem says, all right, and the top of the waterfall is 1.8 meters high. 1.8 meters high. All right. So let's see. Leaving the water vertically. So how long is it in the air? So we've got two parts in this problem. The first part where the trout is going up, and the second part where the trout has landed and he's in the water. Hey, there's the trout in the water. He's happy. All right, so we need to first, let's just calculate the first part here. How long does it take to go up? Okay, well, what equation of motion should we use for this first part? What could we use? Is there more than one?
You could use the final velocity equals the initial velocity times or plus a delta t.
Let's see. So you were saying, let's check it out. So you're saying the final velocity minus the initial velocity equals what?
Acceleration times delta t.
Acceleration times delta t. All right, because we know that for the first part, we know his initial velocity, right? So this is going to be his initial. The final velocity is going to be 0. Final velocity is equal to 0, and then we know his acceleration. So for the first half, we could use this one. What about for the second part? Could we use that for the second part? We can't use this one for the second part because we don't know what his final velocity is going to be when the trout hits the water, right? So we'd have to use a different equation for that one. Now, another strategy would be that we could say, all right, if we look at, so there's a couple ways you can skin a trout. That was fun. Skin it. So you could do it this way for the first part, but that'll just tell you how long it takes him to get up here. For the second one, and I guess we're assuming that it's a boy trout. Actually, it's probably a girl trout because the girl trout is the one that lays eggs. So we should be calling it or her. Okay, so then we'd still have to use a different equation for this one. If we go from the top down here, because then we're going to have to use distance. So maybe it would be easier in that case. Let's think about a different equation that we could use. We could use, let's say, oh yes. All right, we could use the equation where we have delta y is going to equal Vy times delta t plus 1/2 a times delta t squared. Now, why would we use this one? Because there's going to be two solutions to this problem, okay? It's going to go, first it'll go up past 1.8, but then when it's coming back down here, it's going to have another solution that equals 1.8 meters into that in this equation. So you should get 2 times. Does that make sense? Does everybody understand why you'll get 2 times when it's at that height?
But wouldn't one of the times be negative? Because that'll give us a quadrat. Actually, never mind.
Yeah, we're not going to have negative time because we're saying that when the fish jumps out of the water, that's t equals 0 for the purposes of this problem. Okay, but yes, you might have to use the quadratic equation, and so let's take a look at how we do that real quick. All right. So here's our equation. Hey, and we're just going to keep this symbolic for now. But the quadratic equation will give us two solutions. Okay, and we're gonna solve for t. So we'll get this all on the same side here. We'll say 0 is going to equal minus delta y plus vy initial times delta t plus 1/2 ay times t squared. Okay, so does anyone remember how to do the quadratic equation? So let's say if we have a yes, so we'll say a plus bx plus cx squared equals 0. If you have a polynomial like this, you can use the quadratic equation, and the solution is going to look like this. The solution to this will be x is going to equal minus b plus or minus b squared minus 4ac divided by c.
The whole thing divided by 2a, right?
Oh yeah, 2a. Wait, is it 2a or?
Well, I think that's because most times the coefficient for x squared is usually a, so that's why it will be 2a. So I think it should be ax squared plus bx plus.
Oh yeah, you're right. Let's forget that. Yes. Sorry about that, guys. Yes, thank you, Timothy, and who else said that? All right. Well, thank you for both of you for correcting me. Yes, that's right. I wrote it backwards. I'm sorry about that. Yes, forget this part. There we go. This is right. So 2a. All right. So we've got that up here. Okay. All right. So if we plug this into our quadratic equation, okay, so in this here, all right, I'm going to solve for t. I'm going to get, this is going to give me delta t. Okay, and let's put this in here. So in this one, b is going to be vy. So I'll have minus vyi plus or minus. Then in here, I'm going to have vy initial squared minus 4 delta y times 1/2 ay. Okay, and then down here it's going to be 2, and then I've got 1/2 a, so times 1/2 ay. Okay, so my 2's will cancel there. Then this will just become a 2. Okay, so now I can plug in my numbers. My initial velocity is going to be minus 8 meters per second, plus or minus vy, so that'll be 8 meters per second squared, minus, and I've got a 2 times the waterfall height is 1.8 meters, so it'll be 1.8 meters times this is minus 9.8. Wait, is this supposed to be plus or minus in there?
Minus is correct.
Okay. Yes, I think it was. Okay. then divided by minus 9.8 meters per second squared. And that's meters per second squared. Okay, so I'm going to get two solutions to this. If I plug this into Mathematica, okay, I'll get two different solutions to this problem. One's going to be bigger and the other one's smaller. So let's plug these in and then I'll let you go because Mathematica. All right, but I think you see how to do it now. All right, so first we'll have minus 8. We'll do the plus solution. This will be 8 squared minus 2 times 1.8 times a minus 9.8. Oh, what did I do? There we go. Then this whole thing is divided by minus 9.8. Okay, so this says 0.2 seconds, but then for my second solution, I'm going to change this to a minus sign. Okay, so these are both valid solutions to that equation, but I know that the first one is when the trout is ascending, so when it's going up. So the correct solution would be this one, 1.36317 seconds. And I need to round that off to have the right number of significant digits. So my final answer is going to be 1.4 seconds. Okay, and it's going to be this minus solution there. That's the one that's going to give me the answer. Okay, so, all right. Now, this one took me a few minutes, so I don't know. How long did it take me to solve this one? Was that like 15 minutes? Okay, so probably not going to have a full problem like that on the exam because I think that will take too much time. But you should still know how to do it, okay? So, but I think that's probably enough for now. So these are, I think if you know this stuff, you should be okay for the exam. Oh, my battery's about to go dead. Oh no.